Welcome to the GatesAir Introduction to Broadcast Transmitter Technology e-learning module. In Pod 2, we'll cover classes of amplification, impedance, GPS frequency references, personnel safety, AC power, and RF harmonics. As we saw in Pod 1, the source power will equal the desired power output plus the undesired inefficiencies of the transmitter system. These inefficiencies are in the form of heat. The thing to remember is that if you feel heat, that is waste, and you paid for that heat at the power meter. Plus you pay to remove the heat from the equipment and the building. Air conditioners have to be oversized when you are dumping a lot of heat into the room. Let's look at classes of amplifiers. For Class A amplifiers, they are the lowest distortion, most linear amplifiers. They're conducting for 360 degrees, which means they are the least efficient. They make very good audio amplifiers. Class B amplifiers are conducting for only 180 degrees of conduction, which means they're reasonably linear and much more efficient. By themselves cannot be an audio amplifier, but if two are used back to back, fairly linear with a little bit of crossover distortion. Class AB amplifiers are conducting more than 180 degrees but less than 360 degrees, which means they are very linear, much like the Class A, and much more efficient like the Class B. Class C amplifiers are conducting for less than 180 degrees. They're very linear for FM and unmodulated RF, and much more efficient because of their conduction angle. Class D amplifiers are similar to Class C, except they run in switch mode, which means they're on or off, or they're fully saturated or in cutoff, which increases their efficiency. The Doherty amplifier is a form of Class B amplifier, except there are two amplifiers in the Doherty. One amplifies the low-level signal, the other amplifies the peaks. The benefit is the power efficiency and reduced costs. In the Doherty amplifier, the main part is fully utilized and is only amplifying for the main part of the carrier. The peaking amplifier is only turned on when it needs to handle more peaks. So when it's not turned on, it's not consuming power. This is a simplified circuit of the Doherty amplifier. You see the input comes in and split, goes to the main carrier amplifier, and also to the peaking amplifier. The output of those two, again, are combined. Here you can see the summed amplifier from the two parts of the Doherty. In the center is the main amplifier, and you can see on the peaking amplifier it is only turned on when necessary. Now let's look at impedances. RF circuits need to be terminated into a load to prevent the RF energy that's traveling down the line not to be absorbed, which would then be reflected back to the source. The types of impedances are resistive, capacitive, and inductive, and the three main components are the resistor, capacitor, and inductor. Electric current can flow through a circuit as DC, or direct current, or as AC, alternating current, or RF. The impedances in DC and AC circuits are both measured in ohms. A resistor is a passive component. It doesn't produce or consume any electrical energy, but converts it to heat. In DC circuits, the linear ratio of voltage and current is called the resistance. In AC circuits, it's called impedance. An inductor is also a passive component. In the inductor, appears as a short to DC, like a straight wire. As the frequency goes up, the impedance goes up due to the magnetic field that builds up around it. A capacitor appears to be an open to DC. DC cannot flow through a capacitor, so it has a high impedance. As the frequency goes up, the impedance in a capacitor goes down. The capacitor stores energy between its plates. Impedances of capacitors and inductors in a circuit depends on the frequency. The impedance of an inductor is directly proportionate, whereas a capacitor is inversely proportionate to the frequency. For DC circuits, an inductor appears as a short, and the impedance goes up as the frequency goes up. Inversely, a capacitor appears as a DC open, and the impedance goes down as the frequency goes up. The main difference between a capacitor and an inductor is the inductor uses stored energy in the magnetic field, whereas capacitor stores energy in the electric field. Time references in equipment sources from GPS and other frequency references. There are several different reference frequencies used as clock pulses for the operation of equipment. Two are using global satellite sources. One PPS, which is typically will come from a GPS receiver, or some equipment has built-in GPS receivers, so all you do is hook up a GPS antenna to it. Both of these are highly accurate and can be used to synchronize transmitters in different locations, since the source is coming from a common satellite. This can be used as an SFN, or single frequency network, to cover long odd-shaped territory. One prime example of a SFN is along the California coast. To the west is ocean, to the east is a mountain ridge. There's no need to put power in those areas, so by placing small transmitters along the coast on the same frequency as a vehicle is traveling up the coast, the receiver would seamlessly switch from one transmitter to the next with no interruption of service. Other frequency references are used as internal clock pulses used in equipment. External 10 MHz can be used for all equipment within a facility, and internally, oscillators OCXO are used for internal reference for the oscillator. The 1 pulse per second, or 1 PPS, is generated in the atomic clock of the GPS satellites and is extremely accurate and stable. The signal level is 0 to 5 volts DC. The pulse width is 100 milliseconds and repeats every second. GPS satellites orbit every 12 hours. In 1973, the Defense Department combined its satellite navigation system, called Navstar Global Positioning System, or GPS. Later, it was allowed for public use. In 1982, the Soviet Union launched a similar program called GLONASS, Global Navigation Satellite System. Your receiver will always pick up the nearest satellite. GPS delivers extremely precise time references for transmitters. Newer transmitters have a GPS-disciplined oscillator for the carrier frequency, also for external test equipment use. A crystal oscillator is an oscillator circuit used to keep track of time and provide stable clock signal for digital integrated circuits. Environmental factors such as humidity, pressure, vibration, and temperature affect the precision of the crystal oscillator's frequency. To limit that, there are two popular versions of temperature-compensated oscillators, TCXO and OCXO, to help stabilize the temperature. To summarize, frequency references are used for several different applications in broadcast transmission: the transmitter frequency, an SFN network, and the date and time. Now let's talk about safety and lockout, tagout. When it comes to personnel safety, you are ultimately responsible for your own safety. The uncontrolled release of hazardous energy, could be kinetic, electric, or hydraulic, causes over 100 deaths per year. Hazardous energy is not just limited to electrical. It can be hydraulic, pneumatic, mechanical, chemical, and thermal. A good lockout-tagout program consists of a survey to identify potential sources of hazard, procedures for each of those pieces of equipment, a written program, employee training, standardized devices so everyone knows how to lock out a piece of equipment, and periodic self-inspections to make sure everything is done correctly. OSHA standards requires all employers to have written site-specific programs. written procedures for each piece of equipment to be serviced, which is reviewed annually, and employees be trained and retrained on lockout-tagout procedures. This standard does not apply to work on cord and plug connected equipment when the plug is under the control of the authorized employee. It also does not apply to construction, ag equipment, oil and gas well drilling, and service. An affected employee is one whose job requires him or her to operate or use equipment on which servicing or maintenance is being performed, or to be in an area where such servicing and maintenance is being performed. An authorized employee is the person who implements the lockout and tagout on the equipment to perform maintenance or service. Servicing or maintaining activities include constructing, installing, setting up, adjusting, inspecting, and modifying the equipment. Maintenance, including lubrication, cleaning, or unjamming equipment, anything where an employee may be exposed to unexpected energization or startup of the equipment or release of hazardous energy. Remember, lockout-tagout is only for equipment that is not plug and cord connected. It's when an employee locks out a piece of equipment, blocking the flow of energy to the equipment. A keyed padlock will secure the switch or lever. It prevents the machinery from being turned on by accident. And if it's not possible to lock that out, then a tag only is required. Always use lockout-tagout when repairing electrical circuitry, performing other than routine maintenance or repetitive jobs, clearing jammed or blocked machinery, when rebuilding equipment, and during equipment setup. Also use lockout-tagout when there are unused panel boxes in the area. Always communicate with the affected employee that lockout-tagout is going to be utilized and why. Review the survey log to determine the type and magnitude of energy that's being used and thoroughly understand the hazards involved. Shut down the equipment by normal stopping procedures and attempt to operate it to make sure it is fully turned off. Then isolate all the equipment's energy sources. The authorized employee will then lock out and tag out all energy sources and maintain possession of that key. Fill out the appropriate information on the tag, including your name, date, and type of work being performed. The authorized employee will also release any restrained energy from capacitors or mechanical. Make sure no personnel are exposed to hazards, and then operate the normal controls to make sure the equipment is off. Return the controls to the normal, neutral, or off position. The device can be anything that physically prevents the transmission or release of energy, including manually operated circuit breakers, disconnect switches, glides, slides, valves, and blocks. This shows an example of lockout-tagout equipment with locks, a hasp with multiple holes for multiple workers to put their own lock on, a name tag, and other assorted blocks. After the work is completed, ensure that all tools and debris in the area are cleaned up. Check to make sure all the guards and covers are reinstalled. Notify everyone who works in the area, the affected employees, that lockout and tagout will be removed. Then remove the lockout-tagout device and operate the isolation device to restore the energy. So to review the procedure for lockout-tagout, prepare for shutdown. Turn off the equipment and isolate the energy sources. Lock out and tag out those energy sources. Check for residual energy and verify energy isolation. Let's review AC voltage. For single-phase alternating current systems, there is only one AC voltage source. This is common to most household electric power. There are two wires, one hot and one neutral. The load completes the path and gets the work done. In the United States, 120 volts is the standard single-phase voltage, with one 120-volt power wire and one neutral wire. In some countries, 230 volts is the standard single-phase voltage, with one 230-volt power wire and one neutral wire. In the US, most household voltage is dual phase, 240 volts plus a neutral, where each hot lead to ground is 120 volts and each one is 180 degrees out of phase from the other. Here is an example of two-phase alternating current. With three-phase AC, there are three AC voltage sources 120 degrees out of phase with each other. Here are schematic examples of three-phase Y, 4-wire, and a delta setup. The power output of a three-phase system is consistent, whereas with single-phase or even split-phase, the voltage at times will be at zero. And we've all seen high-tension power lines in the country. Here's a quick comparison of a three-phase and a single-phase circuit with the same loads. Notice for three-phase, the current is much lower per leg than the single-phase. Thus, the wire for the single-phase would have to be much larger. Here's a quick comparison of single-phase to three-phase. Single-phase is better suited for less than 1,000 watts, has a simpler design with fewer costs and more applications. Three-phase has greater conductor efficiency and more power capability. Now for a brief introduction to RF harmonics. Harmonics are the undesirable voltages of the frequency that you're trying to amplify. There'll be multiples of that frequency, 2 times, 3 times, 4 times, and so forth. What causes these undesirable harmonics? A common source is the nonlinearity of the amplifying devices themselves. Other producers of harmonics include byproducts of trying to amplify multiple frequencies through a common device. In that case, you get the two original frequencies, the sum of those two frequencies, and the difference of those two frequencies. All of those harmonics are typically undesirable. In digital broadcasting, there are many different frequencies that are being amplified by the transmitter PA, which does create undesirable harmonics. Here we see a chart of the original frequency, f sub 0, and the harmonics 2 and 3 times. Notice they are measured in decibels relative to the carrier. We will get into that in a later session. Thank you for joining us to the Introduction to Broadcast Transmitter Technology e-learning module. We look forward to seeing you in Quincy.